Hi everyone, my name's Helen Rutlidge and today I'll be talking to you about what caves can tell us about groundwater recharge using a decade's worth of critical zone data. So why do we care about groundwater recharge? And it's because especially in semi-arid and arid environments, groundwater is an essential water source. And so this source needs to be sustainably managed, and to do this we need to know essentially how much water is entering our aquifers. And this is hard to measure because it's occurring in the subsurface and there's uncertainty in terms of the spatial and temporal extent of groundwater recharge. When we're talking about groundwater recharge, there's two types. So there's this focused recharge, which is occurring directly from a water body, whether, for example, a river or a stream. The other type is diffuse recharge, which occurs from rainfall entering the subsurface, and then a portion of this makes its way down to the water table and into the aquifer. For this project, we're going to be looking specifically at the timing and spatial extent of diffuse recharge events using caves because they give us the ability to see essentially what's happening in the subsurface, but we're not going to be looking at the volume of the recharge. So this work was done at Wellington, which is west of Sydney. And at this Wellington site, we have the Wellington Research Centre as well as the Wellington Caves. And then at the Research Centre, we have a vast number of bores. So we've got the Macquarie River here. We've got these river flat bores, which are highly connected with the river. And then we've got these hill slope bores over here, which we believe do not have any connection with the river and hence only essentially are recharged by diffuse recharge. And so these are the ones we've focused on for this project. Especially as when we're looking at caves, their mechanism is also going to be diffuse recharge. So if we're looking at diffuse recharge, the main driver of this is going to be both rainfall and the antecedent conditions. So to have an idea of the antecedent conditions, we've looked at the soil moisture. And this soil moisture data has come from the Australian Water Resources Assessment Landscape Model, which is available through BOM. This is a general gridded model, so it doesn't take into account the specific geology of a particular site, but does give you data for across Australia. So this rainfall data here has come from the nearby BOM town station, and then we can see that we have periods where there's significant rainfall where we start to see increases in the root zone soil moisture, which is 0 to 1 meters below ground, but not all of that then makes its way into the deeper soil layers, which in this case is 1 to 6 meters below ground, and some of it tends to be lost mostly to evapotranspiration. And then we can see that when we look at so this is a subset of the groundwater bores at the Wellington Research Station, we have this significant recharge event in 2016, which corresponds with a significant increase in the root zone soil moisture as well as an increase in the deep soil moisture. And so then if we have a look specifically at what's happening in the groundwater time series, we can start to identify potential diffuse recharge events based on two criteria: that there's been a response in a majority of the bores at that particular time point, as well as they have this characteristic shape of a steep increase followed by a longer recession. Doing this, we've identified 14 potential events with this cluster in 2016, which also corresponds with the time period of the most significant recharge. However, we also can see that there's some of these smaller events in 2018, which, if you remember back here, didn't necessarily correspond with any changes in the deep soil moisture, and in fact was associated with a quite significant drought. We then had to dig through the records a little bit, and we've worked out that this is actually due to an irrigation leak at the site and not diffuse recharge. So we've ignored these for the rest of this project. So now that we know what's happening in the groundwater, we can compare what's happening with the caves, because we can essentially see the caves is giving us the ability to see when there's periods of diffuse recharge, because at this particular site they're not influenced by a stream. And so whenever there's dripping from a stalactite, that is essentially water that's made its way through the subsurface and then into the cave system, so i.e. diffuse recharge. And we can measure this using a drip logger, which essentially measures the number of drips. So we've placed a whole network of these down in what's called the South Passage in Cathedral Cave, which is 25 metres below ground. And then we have determined when there's been recharge events based on an increase in the number of drips per 15 minutes across majority of those drip loggers down in South Passage. And doing this, we've identified 12 events which compare quite well with those events that we identified in the groundwater. And so in total, we have 15 events. And there's 4 that are not common or do not appear in both. So 11 are common between the caves and the groundwater. However, one of those events that's not common, whilst it's not seen in the cave, it is seen in the bores that are nearby that cave. And so that leaves 3 other events which are not common. 2 which they only appear in the groundwater and not in the caves. However, this event number 13 is associated with quite high rainfall totals, which would suggest that it's potentially a diffuse recharge, maybe only localized to the research station. And then we have this other event here, which is only seen in the caves. So we were dug into this a little bit more to have a look and to see what is driving the periods of diffuse recharge. And what we saw is that the recharge events tended to be associated with low pressure troughs, and 7 of the events, specifically the one in March 2012 and then that cluster in 2016, occurred in the wettest months in the instrumental record. And then that cluster in 2016 also occurred during a period when the Indian Ocean dipole was in a negative phase, which is what tends to drive significant amount of rainfall. But if we're looking forward, at this stage, it's unclear how the frequency and strength of negative Indian Ocean dipole events will change, especially due to climate change. And it's also not necessarily clear whether, for example, if we start having less strong negative Indian Ocean dipole events, whether therefore we would then not be getting the conditions that are conducive to getting that significant rainfall, which leads essentially to really that one significant recharge event in that 10-year record. So since this is also looking at collaboration opportunities as well, the NCREST Groundwater Infrastructure Program, which is essentially what has provided all of the data, especially at the Wellington Research Station that was used as part of this project, gives researchers access to the data. So in addition to the Wellington, there's a number of other sites as well, including some in the Maules Creek catchment, also in New South Wales. And there's also access to field sites, which people can use for a range of different sampling. And we've had colleagues do work for the ecology sampling, as well as physical and chemical sampling. If we look specifically at the Wellington NCREST site, one of the advantages of the Wellington site is the fact that at that one site we have bores that are in the alluvium, fractured rock and karst environments, and so you can start to look at the differences between those different environments. It also has a research station on site, which gives you a base, whether it be for research or teaching. And it's now also one of the new Australian sites as part of that network of critical zone observatories, which is providing common instrumentation at all of the sites across Australia to look at climate, groundwater and subsurface processes.